Okay, so this is the design for the current portion of the meter for the power supply. And I forgot the decimal point circuit, but that's not a big deal. That'll come. We'll make sure not to forget that on the board. So I have the AC source, and we split the rail into a voltage doubler. And this is a common ground to this common ground to these common grounds to these common grounds. So all these grounds are common, okay? Then we need a trim voltage for the op amps, and we need 200 millivolts, and we need 2 volts. So we have this range here, and we have these two trim pots. So they're going to feed approximately 200 millivolts to here, and approximately 2 volts to here. So when the current flows through this resistor, it'll create a voltage differential. And when that voltage differential at 2 amps is detected, it'll compare the 199 to the 200, and it'll subtract the 2. This is actually a subtractor. It'll subtract the 2. And if we just get a little bit beyond the hysteresis of the op amp, then he'll go, I've got a more positive than negative, and so he'll energize the transistor, and there should be a buffer resistor here just to limit the current. So that's missing. So there should be a 1K ohm resistor right here. So he'll energize the relay, and the relay will close to the next range. Now we bench tested this. These two should be about 9.9K, but we came up about 50 ohms short. So this is just to adjust us in to 9.903K. And we'll probably have to do the same for the 90K resistor stack. So we'll add a adjustment resistor place in here similarly, just so that if we need to, we can put a resistor in. If we don't need a resistor, we'll just put a jumper in. So here you can see when we have up to 200 millivolts, it's going right into the DMM because the DMM takes up to 200 millivolts. Then as the current increases, the voltage increases, and we go into the next range and then the next range after that. So we have 9 volts for the DMM plus 9 and ground that'll go to the DMM for power. And we have signal to the DMM, ground, signal. Then we have these Zeners to drop the 15 volts down to 12 because we don't need a tremendous amount of voltage to do the adjustment here. This actually gives us more precise control because we're only dealing with an adjustment spanning 6 volts, not 30. So it takes out a lot of that dead space. This helps prevent you from having to do a microscopic turn to get the voltage you need for precise control in the op amps. And this is the voltage sense coming in to the op amp. This is the set point, so it's going to subtract the sense from the set point. A little bit more going on in this circuit, and of course, like I said, we need the decimal point control too, so we gotta remember to put that on the board as well. And the plus and minus 15 go to the op amps, so can't forget that. So that's about it for the current control. Oops, sorry, I'm shaking. So we'll try and squeeze the current board and the voltage board all in one board, and it'll be pretty cool because this will change the decimal point and the range automatically depending on the input. It's always neat to make the meters do things automatically.